We are going to continue with talk of Pavel Fileviez Perez. Where is he? Young man, a little bit faster, we are late. Okay, Perez is an assistant professor here at CASE. So, since recently, he has studied in Cuba, in Havana, and in Italy, Trieste, and in Germany. And he received his PhD at the Max Planck Institute for Physics in Munich. He did work as an associate scientist in the particle and astroparticle physics division at the Max Planck Institute for Nuclear Research in Heidelberg, Germany, and he is a visiting associate in the Division of Physics, Mathematics and Astronomy at California Institute of Technology at Caltech. He was a James Arthur Fellow at the Center of Cosmology and Particle Physics in New York, and a Dirac Fellow in the University of Wisconsin Madison. Now, his main research interests include particle physics, cosmology, physics beyond the standard model, unification of gauge interactions, supersymmetric theories, neutrino physics, dark matter in the universe, and new particles at the Large Hadron Collider. I think it's a big flower of interest, and I must admit you are young, much younger than the average of here, if you take away the students, and we have a lot of hope that at least one of your items will come up as a real discovery or as a new line of development. So please.
Thank you very much. It is really a great honor to speak here, to see many of my heroes. And I will try today to talk about physics beyond the standard model. Okay? Then, we have the standard model of particle physics. We can say that thanks to the LHC, we know how all the fundamental particles they get mass. And the spontaneous symmetry breaking is working in nature, and this is how we generate masses. Okay? This is, thanks to the great experimentalists that were made this possible, no? And at the same time, we can say that the standard model provides a very good explanation for most of the experiments, okay? And of course, there are things that I will talk about, but this is a really great idea, a great theory. There is nothing better than that so far. And I would like to say we should say happy birthday to the standard model. Okay? This is why we are here. Now, the situation in the field is a bit confusing. No, because from one side we have a very beautiful and very impressive theory where you can explain most of the experimental results, excluding neutrino masses. But, and then, in the theory community, since the people try to make a contribution, they try to follow different ideas. And as humans, we try to cluster different groups. You could say maybe this one is people that like supersymmetry, and different clusters. Huh? And every time that there is a small anomaly in any experiment, means that, one of these doors, they have a small hole, people try to see what is coming out. But the doors always close. And they don't look very strong, but there is nothing so far, excluding neutrino masses. And this is more or less the situation in the field. People try to follow some ideas, and there is a lot of politics and the taste of different scientists, and they try to see if there is a small door that opens, and maybe there is a new standard model soon. Okay? I would like to say in this talk, in the first part of my talk, I will be in one of these clusters. And the second part, I will be one of these small guy there alone. Just to try both to see how much I learn. Okay? Then, in this talk, I cannot cover too much about physics beyond the standard model, but I will talk a little bit First question that you should ask, what is the origin of neutrino masses? We know today the neutrinos are massive, and in the standard model, as the standard model was built, there is no neutrino mass. Okay? Then this is a clear way. You should add something to the standard model. Maybe the modification is very small, but you have to do. Second question that I will talk about is why the standard interactions are so different. We have the electromagnetic, the weak and the strong, they are quite different. Okay? I will talk about that. We know all the masses, and we have no clue. We cannot predict the values of the masses. You have the ratio between the top mass and the electron mass is like 10 to the 6, and we have no idea about the masses, okay? Nobody has. And then we have, today we know that there are 3 chiral families for fermions. And especially after the Higgs was discovered, we know the cross-section of the Higgs production very well, and then we cannot really add extra fermions for fun in the standard model because you will destroy the property of Higgs. Then this is a very interesting problem, that is you have 3 chiral families, we have no idea why is that. Okay? We discovered the Higgs boson with mass of 125 GeV. Many people have many ideas to explain why the Higgs is light. This has been, also in a very active area, which I will actually not talk about. And if you go to cosmology, some people think that you should go beyond the standard model to think about dark matter. You actually can debate this question, okay? And the last question that I want to mention is that we call us matter, and we don't see the antimatter guys around. Then the standard model doesn't provide explanation for matter and antimaterial symmetry in the universe, and this is a clear way to go beyond the standard model. Here, the main ideas are leptogenesis or electroweak phase transitions. In both cases, you have to go beyond the standard model. Okay? But as I said, there are many, many questions, CP violation, the origin of CP violation, many, many things that I cannot cover in this talk. Then I made this choice. I will talk about neutrino masses, and I will try to answer this, talk about this question, okay? Then let me talk about the first. This is an experimental fact. Neutrinos are massive, okay? And then the question is, what is the mechanism behind neutrino masses? We know that the charged fermions, all the fermions in the standard model, excluding the neutrino, we know now how they get mass, okay? But we don't really know what is the mechanism behind neutrino masses. And if you ask this question, you should say, okay, how do you test the theory for neutrino masses? Because we would like to know, okay? Maybe there is a new symmetry breaking mechanism behind. We should know that. In this way, we can understand the generation masses for all the fermions, okay? Now you go to, many people made huge effort to extract from neutrino oscillation experiment the masses of neutrinos. We don't really know the masses. We know only the difference of the square mass difference. This is a talk that we had here by Professor Kajita, and we know with actually pretty good precision the difference between the masses and so on. And again, the experimental fact is the neutrinos are massive, okay? And now you open again a door. There are many theoretical ideas that you should use to explain neutrino masses, no? Then there are 2 main possibilities. Maybe there are Dirac fermions. This means that you have to impose the conservation of B minus cell. B minus cell is conserved in the standard model as a good global symmetry. And in this case, you just have to add right-handed neutrinos and assume that this symmetry is conserved, and then using this small Yukawa coupling, you can say the neutrino have mass proportion to the back expectation value of the Higgs. And again, here you assume B minus cell conservation, and of course you can try to go to explain maybe a bit more, but this is pretty much the one possibility, okay? But they can be also Majorana fermions. In that case, on top of this Dirac coupling, you have a Majorana mass. And then the existence of these 2 terms tell you that B minus cell is broken now. And then it's no symmetry anymore of the theory. Then this tells you that if you look for B minus cell processes, that tell you that the symmetry is broken, you could maybe point out how to test the mechanism for neutrino masses. These are the main possibilities. Now, I will talk mainly about Majorana fermions. Here, there are many ideas. The main idea behind Majorana fermions is related to the seesaw mechanism. And there are many seesaw mechanisms. I will talk about only one. These are the fathers of the field, pretty much. I told you, you write the Yukawa coupling, and you have a Majorana term, no? This is called type 1 seesaw, okay, for experts. And type 1 seesaw tell us that the neutrino mass is equal to the Dirac mass, that is proportion is this Yukawa coupling, the back expectation value of the Higgs, and suppressed by this mass scale, MR, okay? The point is that this toy model doesn't tell you anything what is the Dirac mass and what is the MR, okay? Then if MD is around the Letroux scale, you find that this scale is very large, okay? And many people like that because they say, oh, this is close to the grand unified scale, and this is nice, and so on, and this is true in grand unified theory. But the truth is that if this is the case, okay, this is called the canonical seesaw scale, we never will test this in any real experiment, okay? There is no way to test this if this is the case. It will be very sad because we know how the other fermions get mass. We don't have access to this scale, okay? We cannot build any collider to produce this if this is the case. However, maybe this is not the case. Then in the 80s, Kuhn and Senjanovic, they actually, even in the context of some left-right symmetric theory, they have a very generic idea. They say, of course, this is breaking B minus L, then you should look for multi-lepton processes at collider, same sign leptons, which tell you that the symmetry is broken, and then you can look and see if you can test the mechanism behind neutrino masses. This is only possible if the right-hand neutrinos, let's say they're around TB scale, then if you think at the Large Hadron Collider, you could maybe test. And of course, in this case, it's possible only if MD is actually smaller, okay? But this is in general possible, we don't really know, depends of the UV completion that you use. And then, again, the question here is that the stability of the theory of neutrino masses is actually crucial to understand how all the fermions get mass. And again, this is a clear modification of the standard model. It's the only solid modification that we can say we have to modify the standard model. How? Okay? Again, but it's very confusing because if this is the case, we never will test the mechanism behind neutrino mass. There is no way. Okay? But maybe this is the case. And then I personally spent some time looking for some arguments to be in this situation, okay? Where this, typically what happens is that you can, for example, if you go to grand unified theory, this is the case that very often the scenario that you will achieve, you have to break a grand unified theory, and you will see that the seesaw mechanism, if you want to be consistent, the seesaw scale will be very large. And again, you cannot test that. But I personally spent time looking for something that tell me that maybe this is possible, okay? Then I tried to find everything that I found, you know, and I tried to go now to cosmology and see if cosmology helped me to tell me, oh, maybe you can test the mechanism behind neutrino masses, okay? Then what I mean by that is I mentioned to you that this is a study that I did when my graduate student. And here I told you, if you have Majorana neutrino, you break B minus L. But before that, if you want to understand the origin of this Majorana mass, you can actually gauge B minus L. It's a local symmetry. Then you follow the standard model, you do a spontaneous symmetry breaking. And then at the same time, you can assume that the dark matter, the mechanism to produce dark matter, is defined by the same symmetry, B minus L. Okay? If you do that, you realize, and this is a pretty simple model, you just have a Berthollet fermion, And when this new Higgs breaks B minus L, you generate the Majorana mass, and then you have the seesaw mechanism. But the interesting thing is not to write any generic model or whatever. It's just you will see that since there is a link between dark matter and neutrinos, you realize, as I said, the masses are related now. This is the mass of the new gauge boson that define basically the symmetry breaking scale for B minus L, and the mass of the right-hand neutrino. You do the calculation using cosmology, and you pose the condition that you don't want to overclose the universe. You don't want more dark matter that is required. You realize that the symmetry breaking scale cannot be too large. Okay? And this is one example that tells you that maybe the Majorana masses must be below the multi-TeV scale, and then you can actually dream about testing the mechanism for neutrino masses at collider to complete the testability of the mass generation, okay? Here, cosmology forces you to be at the multi-TeV scale, okay? I cannot really tell you where, but at least you can find an upper bound on the symmetry breaking scale. In this, here the symmetry is B minus L that made the link, okay? How to do that? Well, a collider, you will produce through the C prime the right-hand neutrinos. They will decay to leptons and a W, and then since you want to look for lepton violation, you want the same sign leptons, you take the jet from the W, and you study these channels, okay? You can do some calculation, okay? And you realize that if the right-hand neutrinos are below, let's say, TeV, the LHC maybe could see that, okay? Again, here is assuming that cosmology, using anything that I personally know, to be able to say that the right-hand neutrinos that are not at the super high scale, if the same symmetry is relevant for neutrinos and dark matter, they should be at the TeV scale. In this case, they should be a way to test the neutrino mass, okay? And this is something that I personally, I don't want to give too many details because this is a more generic talk, but this is personally something that I really like because, again, for a long time, many people talk about seesaw mechanisms and different ideas to generate neutrino masses, but often the scale can be very, very high, and we never know if this is true, okay? Then what the people should do, by the way, not many people in collider physics study lepton evaluation. And they don't probably, and the reason is because they think that neutrino masses are connected to this super high scale. I will say, here I prove that this can be really wrong. In my opinion, people should investigate way more that, and maybe there is a surprise and we can complete our picture of the generation of masses, okay? And this is one thing that I wanted to talk about neutrino masses, to tell you that this is a clear way to modify the standard model, but it is not clear that we will be able to test the mechanism behind neutrino masses. Here I show you that cosmology can help me, force me to be at the low scale, close to the TeV scale, assuming that there is a strong connection between dark matter and neutrinos. Now let me go to the second question. Why the standard model interactions are so different, okay? Well, here people did a lot. And thanks to the great George I. and Glashow, these are one is the father of the standard model. This is the person, is the father of many ideas for physics beyond the standard model. They say to us that it is possible to say that if you can write a theory where you understand that the strong, the weak, and the thermomagnetic interactions are just different manifestations of the same fundamental interaction at low energy. This means that you could see the different interaction as just different manifestations at the low scale. At some scale, you have just one force, okay? And how that works? Well, they did this in '74. They realized that you can embed the standard model in SU5, okay? This is very beautiful because you have only one gauge coupling here. That's why you have only one force. We know that the standard model describes physics very well below or at the electroweak scale. But there is a sad part now. Okay? It's a beautiful idea that you can unify the forces in only one gauge group. I would like to mention that there is also a very important contribution by George I, Helen Quinn, and Steve Weinberg, where they studied this in a different way from the bottom-up approach. They studied the running of the gauge coupling, and they found that they could meet at the high scale. The problem here is that you say, oh, this is beautiful. You can unify maybe in SU5. This is fantastic. This is a way simpler theory than the standard model. But the problem is that this theory cannot be realized at the TV scale or multi-TV scale. It has to be realized at a super high scale. Then you say, this is very pretty, but you get very depressed again because we cannot build a collider to test the physics related to this grand unified theory. Okay? Let me explain why is that. Okay? Oh, that works in this way. You have the different interactions that are unifying just one interaction. And the quarks and leptons of the standard model, they unify in two representations. It's anomaly free, and you have the standard model Higgs living here, and something to break the symmetry, okay? But the important idea here is actually an idea by Patti Salan. Is that when you try to unify interaction, you unify matter. And in the standard model, you know, the quarks, they have baryon number, the leptons, they have lepton number. When you put together in the same multiplet, you break baryon and lepton number explicitly. And when you do that, you feel the pain. You get proton decay. Okay? Means that there are new interactions in this grand unified theory that you actually can use to get something. For example, the proton goes to positron at pi 0 to 2 photons, and these are a spectacular, this is a spectacular prediction. And even if this theory is realized at the high scale, the people did believe in these ideas. They were able to build many experiments. For example, this is a super Kamiokande experiment, which is a really impressive experiment. And thanks to many experiments, we have all, actually these are the best bounds that we have in particle physics, which tell you that, let's say the pi 0 positron channel, the lifetime should be about 10 to the 34. The K plus is getting close. And this is the phenomena. These experimental bounds are so strong that force you to assume that the mass of the new gauge boson in the grand unified theory should be above 10 to the 14, 15. And then, as I said, you get very depressed because the idea is very beautiful, but you cannot have a direct access to the high scale. Of course, you can, maybe one day we find proton decay, we make a celebration, but we will have a second problem, is that we don't really know what is the mechanism behind proton decay because we cannot have access to this super high scale. Okay? But this is how it works. The idea is very beautiful, but the experiment tells us that you should live far away. Okay? Very far. And this is what, for 40 years, the people call physics at the high scale. And the people say it's very beautiful and everything, but we maybe never will know about this. Okay? Then the original Georgi Glashow model actually doesn't really work. Okay? There are problems with the unification. If you assume the symmetry at the low scale and you do the running to the low scale, you cannot match the value of the gauge coupling at the low scale. There is a problem with fermion masses, that the mass of the down quarks and the charged leptons are the same. And of course, at that time they didn't know about neutrino masses, and therefore there is no neutrino mass. But this, for example, is pretty easy to accommodate. You can actually even take the original model and do modifying. You can generate neutrino masses and achieve unification in agreement with the experiment. Okay? And you can compute the proton lifetime very well. And recently, actually, we studied this in detail, and we proposed a realistic SO5 scenario where neutrino masses are generated through the type 3 CISO mechanism and type 1. And the nice thing about this theory is that the neutrino channels for proton decay, you can actually predict the upper bound on the lifetime of the proton. And even the messenger for CISO has to be light, okay? This is something very beautiful because Hyper Kamiokande, that is the new generation beyond Super Kamiokande in Japan, they could maybe see a signal connected to proton decay. But again, this will be fantastic. This will be really amazing, but it is a pity that these ideas must be realized at the super high scale. Okay? But maybe this is true. You never know. And this is what, again, for 40 years, we call high-scale unification. Very hard prediction is the proton is not stable. Okay? Again, that's why the bounds are super hard. 10 to the 34 years, the lower bound. And high-scale unification, again, the unification takes place at super high scale. Later, you can combine many ideas. You can use supersymmetry. You don't need to do supersymmetry. You can unify in SO10. You can go beyond that. But the whole point always is these ideas are realized at the super high scale. Okay? I am afraid, not even we have access to that. Okay? Again, these are really beautiful ideas, but maybe they are true. We don't know. But if we are true, we will live in a very strange situation that we see new phenomena like proton decay, but we never have access to this high scale. Okay? Maybe that is true. Okay? Now suppose that there is something wrong with these ideas. Suppose that, again, for 40 years, people have been talking about unification, and many people love that. And on top of that, maybe you can put gravity, and there are many ideas for that and so on. But the sad part is that this is always realized at the high scale. Okay? But suppose there is something wrong with these ideas, and you say, okay, why we don't try to think about the possibility to have low-scale unification? Means that maybe unification doesn't take place 10 to the 14 or 15 or 16 GB, maybe at the multi-TV scale. LHC maybe will never see that, but maybe the next collider or the next collider or the next collider. But 10 to the 15, I don't see any collider. Okay? This is a problem. Then how to do that? Okay? The first things that you should do, I told you the main issue is the proton stability. You should write a theory that tells you that the proton is stable at any level of perturbation theory, stable, completely stable. If you are able to do that, you don't have to worry about proton decay bounds, and then you can change the rules of the game. Okay? Then, of course, you should unify at the low scale. But again, this is easier to achieve in the sense that you can play more. Here you have no choice. If you have proton decay doesn't allow you to be at the low scale. And of course you have to change. Maybe you are not able to have a simple grand unified theory, but this will force you to find a new type of grand unified theory. Okay? And this is something that I started with my collaborator, Professor Mark Weiss from Caltech, that he gave a talk today, that we actually started in a very modest way. Okay? We just wanted to understand something totally different. We wanted to say, you know, baryon number is broken in the standard model in 3 units by instantons. If you want to get proton decay, you have to break baryon number in 1 unit. Then in the standard model of particle physics, the proton is totally stable, okay? There is no way to get proton decay because it's broken in 3 units, not in 1 unit. And we say, we would like to understand the spontaneous breaking of baryon number, assuming that the baryon number is a local symmetry, okay? This is a small idea that was in some paper by Abraham Pais that nobody actually used. These are papers that were totally neglected in the community because often people follow more fashion. And we say, I could say that we were the first to write a realistic model for the spontaneous breaking of the baryon number and the spontaneous breaking of the lepton number, and try to do this at the lowest scale in a consistent way with the experiment. And then what we did, we say, okay, let's take the standard model, forget about anything exotic, and assume that this is a local symmetry, okay? And lepton number as well. I will talk only about baryon number. However, as you know, this is, you know that the baryon number is not anomaly free in the standard model. Then if you want to understand the spontaneous breaking of baryon number, better you define a theory that is anomaly free, and then you can study that, okay? And then if you check the anomalies for baryon number, QCD is Berthold-like, and the other anomalies are actually 0, and there are only 2 anomalies which are non-zero, okay? And then you will say, oh, maybe it's not so hard, okay? You have to add something to the standard model, okay? And we study all type of solutions. Thanks to the LHC, these 2 solutions are ruled out, okay? And then I will give you a feeling how that works. Before I give you the details, I can tell you, you can study the spontaneous breaking of baryon lepton number as a local symmetry at the lowest scale. This is consistent with the experiment. Because the proton is actually stable. And on top of that, you realize that in the simplest model, you can have a candidate for dark matter, and you can even try to understand baryogenesis in these scenarios, okay? Something that we didn't actually plan in the beginning, okay? And again, the key point is that the proton in this theory is stable. I will explain how that works. And if the proton is stable, I told you, you could use that as a recipe to go and try to understand a unification at the lowest scale, because you don't have to worry about proton decay bounds. Okay? How that works? The simplest model is you put 3 Berthold-like fermions and the partners. They have baryon numbers, and anomaly cancellation will tell you that the difference has to be 3. This is interesting, 3. Okay? And then you go beyond, and you try to, some of these fields, they have electric charge, they cannot be light. Then they have to get Berthold-like masses, means that they will get masses from the spontaneous breaking of baryon number. Then when you take into account 2 things, anomaly cancellation and generation of masses, you realize that the baryon number for this new Higgs is fixed. It's -3, it's not 1, okay? And then this means that you will break this, and you will get only delta B equal ±3. This means that the proton is stable. This means that you don't have to assume a big separation between the electroweak scale and the high scale, okay? Because if you have any theory beyond that, where you have the median of the theory, the proton will be stable, and then you don't need to assume something that we call the desert. Desert is something very funny, as I said. You have something at the lowest scale, the standard model, and typically we get the grand unified theory or something more exotic, and typically you have to assume that this happens very often, very far away. However, if you have this low energy theory, where baryon number, you have the spontaneous breaking of baryon number in 3 units, this is not needed because the proton is stable, and then you can actually try to change the rules, okay? Okay, the nice thing about this theory is that it has many peculiar and interesting properties that we didn't look for any dark matter, but there is actually a dark matter candidate there. There is a new gauge boson associated with symmetry breaking, which decay to quarks and dark matter. And of course, there is a new Higgs, and you could produce all these things together. And there is a very strong connection between all these signals and the existence of dark matter. And then you could ask me, what is the, if here I prove that you can understand the spontaneous breaking of baryon number, and I tell you it can be at the lowest scale because proton is stable, but it will be nice to know which are the bounds on that, okay? Then, for example, this is a paper from CMS. You can see the new C prime associated to baryon number can be actually pretty light. You don't need to suppress because the QCD background is actually severe, and actually this can be broken at a very low scale. Okay? However, at the same time, I told you there is dark matter, and you can do the analysis for dark matter and see that you're actually consistent with all the dark matter experiments. And there is no problem in cosmology. You can achieve the right Rayleigh density, and direct detection is actually okay. However, I tell you, I can do this spontaneous breaking. The proton is stable. The collider experiments allow me to have this symmetry breaking scale, the very low, around even around the electroweak scale. But you could tell me, yeah, maybe this happens at the Planck scale. You know, then you never can test this idea if this is broken at the high scale. Well, the fact that you need to satisfy the bound on the Rayleigh density for dark matter, there is no freedom here. The symmetry has to be broken below some multi-TV, okay? And you should smile here because this is way below 10 to the 15 GeV. Then there is a hope maybe to test the existence of the way to know if the baryon number is a local symmetry in nature and was spontaneously broken, and see that gives you some information that the proton is really stable. And this is interesting for anybody beyond, you know, anybody building more fundamental theory. This is a very general recipe, okay? And the nice thing is, again, the symmetry must be broken at the lower scale, way below the Gauss scale. Everything here is in 4 dimensions, nothing exotic, very simple, okay? Now you could ask me about exotic processes like delta B equal 3, but they are actually very high suppressed, okay? Then as far my collaborators and me, we check everything that is possible. We never found anything inconsistent, anything cosmology, anything that is and this can be really realistic, okay? Now, as I told you, here we have a theory to explain why the proton is stable. Because if you follow the standard model, you study the spontaneous breaking of baryon number, you realize that the simplest model tells you that the baryon number should be broken in 3 units. You never will get proton decay. This is a good theory using spontaneous symmetry breaking to explain that the proton is stable, okay? If this is true, I told you, you can change a little bit the rules of the game. Because now you can say to Super Kamikande people, thank you, you did a great job, but maybe the proton is stable. Let me try to understand that, okay? And the question is, what about unification, okay? What I mean by that is that in the usual way, we like to have the standard model at the low scale, some unified theory, or something more exotic at the high scale, because the proton doesn't allow me that, okay? Let's see if you can do something better, okay? As you can imagine, it's not so easy, okay? But again, the recipe is very simple. I don't really need to stick to a given theory at a high scale. Anybody can build a theory, but if you do what I said, if you have the theory with local baryon number at the TV scale and it's broken in 3 units, you should be fine, okay? But I will show you what I did so far. Well, the point here is, again, you take the standard model, and you say you have a local baryon number there, okay? And then how to unify that? Okay, the key idea is simple. You know, the quarks, they have color, and they have baryon number. Then let's put them together. It's basically the same idea of Patti-Salan for SO4 color, but in the Patti-Salan idea, you put quarks and leptons together. Here, since you want to have embedded in baryon number, you should put quarks with some new Berthollet fermions. They don't have lepton number. And then you could start using unification in this way, okay? And so far, what we found is that you can write a theory like this, SO4 cube, that is broken to 3 unification with baryon number, local baryon number, and this can be broken to this theory that has to be realized at the lower scale. Okay? Again, this is not so simple like SU5. Okay? It's not complete unification. I just try to give you the best I got and the best that can be done so far, that you can actually have the embedding of this theory in something simple. Maybe this can be embedded in a more fundamental theory or something different, or you are welcome to think about that and find something that look more appealing. But this is so far what we have, okay? And again, if you want to change the rule of the game and try to understand unification on the low scale, make sure that the proton is stable. And as far as I understand, the only way is to do what we did. Understand the spontaneous breaking of baryon number and show that it's broken in 3 units and not 1 unit. But I told you that you have to face the issue that the unify or the partial unification you have is not so simple like SU5. Okay? And let me summarize. I hope, since I am the last speaker, I can speak for 2 hours, right? Okay, this is fine. I told you in this cluster of people I was alone at some point. Let me summarize. I told you that it is crucial to understand the stability of the theory for neutrino masses. This is something that is very important because this is the only way to really complete the picture of how all the fundamental particles get mass. Okay? And I told you, using cosmology, I can motivate the symmetry that tell you how right-handed neutrino masses are generated should be broken at the low scale, and then there is maybe a hope to test this at collider, okay? Then the second part, I told you that the idea of the classical ideas of grand unification, they are beautiful, really, really beautiful, and they are maybe true, and maybe this is how things are. I only try to show you that you can even do better. You can even write theories where you can have even an upper bound on the proton decay lifetime, and maybe Hypercambiocande or any other experiment could maybe see that signal. Maybe this is how it is, okay? And the last part I try to tell you that using a simple idea where baryon number, also total lepton number, is a local symmetry, and you study the spontaneous breaking baryon number, you actually can write a simple theory to understand the stability of the proton. For me, this is a very interesting thing because we don't know if the proton is stable or not. Then it's good to have a theory to explain the case, but it's good to explain that maybe it's stable, and we have a theory for that. Okay? And this can actually maybe change the rules of unification because you are free from the proton decay bounds. Okay? Then I don't know which door will be open. Clearly, neutrino masses tell you there is something beyond the standard model, but maybe there is something that LHC will find soon and we will have fun. Okay? Happy birthday to the standard model.
So thank you very much. We are waiting, looking forward what comes out during your lifetime. So questions, yes.
Have you studied the production of topological defects in cosmological phase transitions when you have such breaking at low scale?
Actually, no, but no, we didn't actually study, but it's actually very similar to what the people study for B-L. Very similar. But we never actually study carefully to see if there is something. I don't really expect something, but it's actually interesting to show this, if there are string configurations and things like that. No? Okay. Many people ask me, but I don't know. I didn't write a paper about that.
You had a question?
In your realistic SU5 model, did you solve the doublet triplet splitting problem?
No, this is an open problem that nobody actually can solve. There is no solution here for the doublet triplet splitting. There are some ideas for doublet triplet splitting, But in reality, when you try to write a full grand unified theory realistic for Fermi masses and everything, we don't really have a solution for double triple splitting.
Another question. For your last, that grand unification theory, that's a semi-simple theory. Why don't you do a simple grand unification, the low-scale unification? That's SU4 cube. That's a semi-simple. Why don't you do a simple grand unification?
You mean like try to? We try, but doesn't work so far.
Oh. Is there any reason semi-simple is better?
No,
simple.
there is no reason. It's that this is the simplest thing that you can do.
Okay.
Okay, and then I give you what is the simplest thing you can do, and then you try to see the embedding something more complete. Okay, this is the simplest you can do. For example, something that I show here, SU3 cube is the maximum subgroup E6, and I break this to SU3 cube times U1 barrier number, local barrier number. And then you could try to think if SU3 cube is embedding E6, how that can be embedded, okay? But it's not so trivial. But this is the way to go.
I had a question about the neutrino part. Actually, I saw a result from the Fermilab recently that said that the mini boom experiments also had an excess of electron neutrinos, just like Los Alamos had back in the 90s. And I was wondering if, because some people are excited that that might be a sterile neutrino, a sign of a detection. I was wondering if you could comment on that.
Well, I mean, I am a theory. What I can say, that will be great to have a new signal and try to, especially it's very low scale, you know, and then that will be fantastic because it's one more element that you could put in the game, no? But we have to wait if this is true or no. You know, we have to see what the experimental community decide to and see if this is really true. But this will be fantastic because it's one more element that you can take into account when you think about generation of neutrino masses.
Okay. Thank you very much, and thank you again.